Hello, I'm Luca Modenese from Imperial College London, and I'm presenting this work about the automatic generation of biomechanical models of the lower limb and how they compare to manually built models. The work was done in collaboration with Jean-Baptiste Renaud from Marseille University. The motivation for creating and using personalized models of the musculoskeletal system is clear in orthopedics and other clinical applications. If we want to provide a therapist with the possibility of studying the effect of a deformity, a surgeon with the tools for predicting the effect of a skeletal alteration, or investigate the effects of different aging on muscles, we do need musculoskeletal models including these personalized features. Currently, generating highly personalized models of the musculoskeletal system is possible, and the required steps can be described by the following workflow. Starting from medical images, normally CT or MRI scans, three-dimensional surface models of the bones are obtained by segmentation. Rigid segments are then defined, assigning an appropriate anatomical reference system and mass properties, which are calculated from the total body mass. Then, on the bone geometries, bone morphological analyses are performed in order to define joint reference systems consistent with the observable articular surfaces. Finally, a musculature model can be mapped to the bone geometries, and using some modeling software such as NMS Builder or OpenSim, a musculoskeletal model is created. This model can be used in biomechanical analysis that use data from clinical gait analysis, ranging from joint kinematics calculation to muscle force and joint reaction estimation. In a recent paper with collaborators from Sheffield University, we proposed a codified approach for the generation of musculoskeletal models that was shared with the modeling community as a step-by-step guide, including the procedure for geometric fitting of articular surfaces, joint reference system definition, and muscle atlas registration. This method, however, has strong limitation if we envision a use of musculoskeletal models in standard clinical application. In particular, this approach is time-consuming, as it requires around 5 hours to generate a single leg model. It also consists of a complex workflow using 4 different software plus MATLAB, and because of that, it requires operator training in order to be executed. Finally, there are still certain operations such as the selection of articular surfaces that are manual, and therefore there is an operator-related variability in the produced models. With the aim of overcoming these difficulties, Jean-Baptiste Renaud and I have created Staple, a MATLAB toolbox, the name of which stands for Shared Tools for Automatic Personalized Lower Extremity Modeling. Staple builds on top of GBOK, which is a toolbox for morphological analysis written by Jean-Baptiste during his PhD. And Staple implements all the modeling operations that are required to create a lower limb model. The models are in OpenSim format and are generated using the Application Programming Interface (API) of OpenSim 4. Here, I would like to make you appreciate the workflow simplification after the introduction of Staple. Again, the segmented bone anatomy and the anthropometric information are required, but now this information is just provided to Staple that in around 30 seconds will generate a model usable for biomechanical analysis. At this stage, we can only generate skeletal models, and therefore the biomechanical analyses are limited to joint kinematics and joint kinetics. In Staple, we have implemented several algorithms from previous literature, as well as designed new approaches to process bone geometries, so that the toolbox really gives enough flexibility for each user to plan their own workflow. You can see, for example, how femur and tibia can be processed using 6 alternative approaches. Because of the intermediate computations that are performed during the bone morphological analysis, Staple also offers additional functionalities, such as bone landmarking, articular surfaces identification, which can be used for implementing more advanced joint mechanics, and model merging capabilities. Our latest update consisted of a mechanism for the patellofemoral joint, based on the model with the rigid patellar tendon proposed by Sanchisi et al. In 2011. This model can be created and inspected using our GitHub repository. Of course, you might ask, Are these automatic models as good as the manual ones? So we have taken 4 anatomical datasets with bone geometries obtained by segmenting CT and MRI scans of variable quality, and for which musculoskeletal models had already been created using the manual step-by-step approach. For these datasets, we have created an automated version of the codified manual procedure and generated equivalent skeletal models. Then, we compare the joint reference systems from the manual and automatic models, quantifying the linear distance between the identified origin and the angular differences among the corresponding axes of each joint reference system. The values that we computed were compared against the interoperator repeatability reported by Montefiore et al. In 2019 for the manual procedure to verify how staple was performing in comparison to the variability of human operators. We found that at the knee and at the ankle joint, the differences between automatic and manual models were comparable to the interoperator repeatability. The reference system of the pelvis ground joint, instead, presented differences up to 3.6 degrees between the two models, due to a different identification of the pelvic bony landmarks. Finally, we found maximum differences up to 11 degrees for the subtalar joint axis. This result was attributed to the very low quality of the processed mesh, and it is not too far away from the maximum variations reported by Montefiore, which were around 10 degrees. To quantify the effects of model differences on joint angles and moments, we simulated 6 gate trials using the automatic model created from the worst quality bone geometries and the corresponding manually built model. We compared the obtained waveforms using a statistical parametric mapping two-tailed t-test. When focusing on the joint angles, we found statistical differences only for the pelvic tilt and hip flexion extension, and they were due to a constant offset of around 3.4 degrees introduced with the pelvic reference system and propagated to the hip. When looking at the joint kinetics, on the other hand, we identified statistical differences between the curves produced by the two models, mostly during the swing phase of the hip and knee flexion extension moments. The differences were consistent with the effect of a 25% difference in shank mass that we observed in our models and was due to the use of regression equations in staple and volume-based mass estimation in the manual model. In summary, hopefully I've convinced you of the value of staple as a tool for the generation of automatic skeletal models in negligible processing time, and of how the biomechanical results from these automatic models compares extremely well with those from manually built models. The use of bone geometries as input is currently a limitation of the approach, as it requires segmentation of the medical images, although this is a technical problem for which solutions have been proposed in the recent literature. The next step, of course, is adding muscles to these skeletal models, and I want to give you a quick overview of what we're planning to do in this regards. Together with Josef Kout from the University of West Bohemia, we have developed an approach to generate three-dimensional complex muscle models from muscle segmentation. This approach is fast, and you can read the details in the open access publication. We are currently working to integrate this approach in staple, so that after creating the skeletal model, muscle attachments based on extensive cadaveric dissection data can quickly be identified on the bone surfaces, and the resulting model can be used for musculoskeletal simulations. The current prototype we have takes around 30 seconds for building the skeletal models, 30 seconds for the muscle mapping, and less than a minute for the simulation. As you can imagine, this represents a huge step forward compared to the previous time-consuming approaches that I've mentioned in the introduction. In an effort towards open science, the staple toolbox and all the code required to generate the results, models, and plots that you've seen in this presentation are available from my GitHub account. All the relevant links and further details and analysis are available in our recent open access publications connected with this presentation. I want to conclude by acknowledging my colleagues at Imperial College London and my source of funding, and I thank you very much for your attention.